Okay, folks, so I'm going to do a little session right now on intermolecular forces, not specifically around how to identify which molecules have them, but more in terms of the qualitative explanations as to how they arise, which is more. These questions have crept into AS exams over the last few years, so I think it is important to spend a bit of time discussing them. So we'll start with van der Waals forces. So I'm going to use this worksheet to help me, and I'll do a few notations as well. So the first thing to notice about van der Waals forces is sometimes they are called these things here. So induced dipole-dipole forces or London dispersion forces in very old textbooks. I actually do think the induced dipole-dipole forces actually do help you explain how these forces arise. So where does it arise? It arrives in any molecule which doesn't have a permanent dipole. So what does that actually mean? Well, let's choose an example. So let's use chlorine, for example. So here is chlorine. And that bond, we would say, is non-polar. It is a non-polar bond. Why is that? It's because that both atoms have the same electronegativity. So the electronegativity of chlorine there and the electronegativity of chlorine there are exactly the same. So remember, think about electronegativity being a bit like a tug of war. So they're trying to pull the electrons, which are in the middle of that covalent bond, towards each other. And because they're the same atom, they've got the same pulling power, effectively. So where do the electrons of the covalent bond on average spend most of their time? Smack bang in the middle, so in the middle of that covalent bond. So it is not polar. All right. However, electrons are fairly mobile things. So what could potentially happen at any one time is that the electrons could be more over here. Now, if the electrons are more shifted to the left, we've gone from having a non-polar bond to a polar bond, but not for very long. This is now what we call a temporary dipole. So we have a temporary dipole. Why is it a dipole? Well, because there's an asymmetric distribution of electron density. Now, these are all big words, so I'll explain it in a moment. So the electrons in the covalent bond are distributed asymmetrically, i.e. they're shifted towards one atom more than the other. So if they are over here briefly, and it would be very briefly, picoseconds, then all of a sudden this becomes delta negative and that becomes delta positive. So we've got a temporary dipole there. All right. Now, what could happen is that the electrons could be shifted over to this chlorine at any one point. So think of the electrons moving rapidly back and forward, back and forward, back and forward, back and forward. So if you were to average their position, it would be smack bang in the middle, which is why we don't say that it is a polar bond. All right, this is a temporary dipole. Now, whilst this temporary dipole exists, let's bring in another chlorine molecule. Okay, so what is this chlorine molecule? What is this temporary dipole here going to do to this neighbouring chlorine molecule? Well, because there's a delta negative and a delta positive, they're going to attract and repel electrons in other molecules. So what you'll find happening is that the electrons in this covalent bond here would end up shifting towards this end. Why would they end up shifting towards this chlorine atom, i.e. away from the middle? It's because of the delta positive chlorine there. So that, obviously, electrons are negatively charged. You've got something here which has a partial positive charge, so it will attract the electrons in this bond towards the end of this molecule here, which means then, once we've finished with that, so if I draw the new position of these electrons, there we go, that becomes delta negative, and that becomes delta positive. All right, and then what we've actually got here is we've got positives lined up with negatives and negatives lined up with positives. So we've got this sort of interaction there and there. So it's a electrostatic attraction, really, between a partial positive chlorine atom there and a partial negative chlorine atom there, and vice versa. So the key thing is, with this dipole here, the dipole on this molecule, all right, was induced. So what that means is that it was forced. It was forced upon. by the temporary dipole above. So the temporary dipole here induced a dipole in this molecule. Oops, sorry, just get the message out of the way. Now that's created these little electrostatic attractions, and these are what van der Waals forces are. Okay, so they exist in any molecule with non-polar bonds because the electrons in the bond are shifting, are moving all the time. So how would we actually explain that? Well, let's have a look here. Okay, so even in molecules with non-polar bonds, there are temporary dipoles due to uneven electron distribution or asymmetric distribution of electron density. This induces a temporary dipole in a neighbouring molecule, producing a temporary induced dipole-dipole interaction. So basically, you could articulate it using actual symbols. So you could actually say that, let's just get a pen here, it creates a dipole, or you could just write it creates this, which induces this in another molecule, and then you get an electrostatic attraction between them. All right. Key thing as well to notice is that van der Waals forces between molecules are affected by size. So the bigger the molecule, so if you look at this point here, the bigger the molecule, the greater the van der Waals forces. Why? More electrons, and you get more points of contact, so you get stronger van der Waals forces of attraction. And I think that's probably the hardest one to explain. Permanent dipole-dipole attractions are the same as van der Waals, just not temporary. They're there all the time. So if we have a look at this molecule just here, okay, so let's look at this. That dipole there is permanent. It is there all of the time because, and this is where you probably have to get this into your answer as well, the difference in electronegativity between hydrogen and chlorine is big, large, vast. Right? There's a big difference in electronegativity between hydrogen and chlorine. You could argue as well that, well, you couldn't argue, you could state that chlorine is more electronegative because it's got the delta negative sign there. So that's basically permanent. It's a permanent dipole. So let's just read our explanation. Some molecules with polar bonds have an overall dipole, although not all do. Okay, so just remember that some molecules will have polar bonds, but not be polar molecules, and that's all to do with symmetry. So, for example, it says here that CCl4 is non-polar. So why is that? Well, if I draw it out, so CCl4 tetrahedral, okay, delta negative, delta negative, delta negative, delta negative, and that's delta positive. So because all of the negative charge, or the partial negative charge, is spread evenly around the whole molecule, they sort of cancel each other out. So even though there are polar bonds, because those polar bonds are all distributed evenly, the molecule is non-polar. Now, how can we turn this non-polar molecule, so this is non-polar, into a polar molecule? Well, just change one of the chlorines for any other atom. So if I change that for, let's go for a hydrogen, all of a sudden the carbon-hydrogen bond is not polar because it has got the difference in electronegativity between carbon and hydrogen is very, very small. All of a sudden now these partial charges are not distributed evenly around the whole molecule. So think 3 dimensions. Molecules are 3-dimensional things, so make sure that you're thinking in 3 dimensions here. This molecule has gone from being non-polar to polar. So now, because it is a polar molecule, it will have dipole-dipole forces. Whereas before, if it was non-polar, it would only have van der Waals forces between its molecules. Okay, so again, you've got your polar bond, and it will attract a neighbour. And again, you could simply draw that. All right, if you drew that as an answer, along with the explanation as to how the polar bond arises, i.e. because chlorine is more electronegative than hydrogen, that is usually more than enough to gain you the marks. And then we come to hydrogen bonding. which is just a very special case, and that's the key thing there, right? It is a special case of permanent dipole-dipole attractions. It's basically when a hydrogen atom is bonded to a very electronegative element, such as fluorine, oxygen, or nitrogen, or NOF as we call it. So the three most electronegative and smallest atoms. So, and you know how to draw the diagrams, all right? So again, articulating hydrogen bonding, I always think it's a little bit cumbersome, but drawing a hydrogen bonding diagram, even if it asks you for an explanation, is absolutely fine as well. So if I was asked to explain how hydrogen bonding occurs in water, I could probably just simply draw a diagram. So delta negative, delta positive, and get my... And then don't forget your lone pairs, they're crucial. So oxygen, let's use a pen. And then showing the hydrogen bond from a lone pair, not drawing this particularly very well, to a neighbouring hydrogen molecule. So there is the hydrogen bond. I only have to show one. But then explaining why are there delta negatives and delta positives here. So simply saying that O is more electronegative than H. So oxygen is more electronegative than hydrogen, therefore a dipole is permanent. All right, so oxygen is delta negative, hydrogen is delta positive, and then describe it. The lone pair on an oxygen atom is attracted to the hydrogen atom on a neighbouring molecule, and that's quite cumbersome. All right, so if you can just draw that diagram and then a brief explanation as to how the polar bond arises, that's usually good enough to get it. And the key thing is, don't forget that hydrogen bonding is not a bond. It is an intermolecular force. All intermolecular forces are weak, but hydrogen bonds are the strongest of the weak intermolecular forces. In terms of, compared to covalent bond strength, if we just have a look here, all right. So here's the order: hydrogen bonding greater than permanent dipole-dipole, which is greater than van der Waals forces. Covalent bonds are very strong, hundreds of kilojoules per mole, whereas intermolecular forces are usually in the units of kilojoules per mole, all right, or the tens of kilojoules per mole. So they're very, 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 very weak. Right. So just to finish off then, let's have a look, just proof of how strong these things are. So if we have a look here, so you can clearly see each coloured line is going down groups 4, 5, and 7. So you can see the general trend for there and there and there is that as you go down the group, the molecules get bigger, therefore you get stronger van der Waals forces between molecules. But the actual smallest molecules in groups 5, 6, and 7, so the smallest molecules have the highest boiling points. So these things here, okay, there, and there, they are the smallest molecules in each of those groups, but they've got the highest boiling points. Why do they have the highest boiling points? Because they've got hydrogen bonding between their molecules. Why? Because there is a hydrogen covalently bonded to either a nitrogen, oxygen, or fluorine, which are the most electronegative elements, so you get the biggest dipole effectively. And that will then draw the diagrams of those things, helps you to explain how they arise. So I hope that helps in terms of just explaining how intermolecular forces arise. And like you say, any other issues that you've got, just let me know, and I'll produce similar videos for it. Okay.